Consider a horizontal slab of air whose thickness is dz. The slab is at rest. That means in order to be balanced, the pressure holding it from below must equal or must balance. It's not a force, so it must balance the pressure from above and the weight of the slab. We need to derive an expression for dp over dz that accounts for the variation of the pressure as we go higher or lower in altitude in terms of the density of the air. Okay, so why don't we go ahead and draw a free body diagram on that slab. This is part A. Let's say that this is the slab of air, and this is an upward view, and or let's just say it's a side view. If it's a side view, so like let's say that this is the slab like this. So the two forces, we have this is the height is dz. So we have a pressure here and a pressure here, and we have the weight. So that's the mg of the air slab, and we know that the pressure is force over area, so that the force has to equal pressure times the area. So we have one above it, so FA equals PA times the area, right? This would be the area right here, and so we would have above it, this is FA, and below it, this is FB, below and above. And so we know that FA, if this is in static equilibrium, the sum of the forces downwards has to equal the sum of forces upwards. So FA plus mg has to equal FB. And so the difference, so that means FB minus FA has to balance mg, and the difference of these forces is just PA or PB minus PA times the area, right? Because pressure is force times area, and I factor out the area. But if dz is infinitesimal, meaning very small, the change is in pressures is a very minute change, and we can call it dp. The differential dp times a has to equal to mg. And so now I could say, if I continue here, part A, so that means dp has to equal mg over a. Okay, so the mass of the slice of air times the gravity over the area. Now we know that the mass is density times volume, so this will be the rho, the density for air, times the volume of that piece, of that slab, times gravity, right, over the area, so this would be area. Okay, and we know that volume divided by area is nothing but the thickness, which is dz. So that means dz or dp has to equal to, so this guy here is the thickness dz, the height, volume divided by area, so this would give me rho of air times gravity times dz, because we said that this here is dz. So now if I divide dp over dz, this would give me the rho air times the gravity. Now notice that in my differential I took the difference between the pressure below and the pressure above, right? So if I reverse this, if I were to switch, I could just switch the sign and say pressure above minus pressure below in order to indicate the change in pressure with height. I'm assuming that height increases as I go upwards. So I'm measuring the y-axis from the bottom up. So that means I would have, if I keep my dp the same, except I reverse this here, I would have to put a minus sign here. And so there would be a minus sign everywhere, and there would be a minus sign here. And so this would be the change in pressure with change of height. Rho, negative density of the air times gravity, which makes sense that measuring from the bottom up, as we increase the height, the pressure would go down. Oops, let me just fix this. Part B, it says use the ideal gas law to rewrite the density of air in terms of the pressure, temperature, and the average mass of the air molecules. And we have to show that the pressure obeys this differential equation here, which is called the barometric equation. Okay, so let me start by writing down the ideal gas law. So I know that pressure times the volume equal the number of moles times R times T. Now the moles is just the number of moles of the air molecules will be the mass total of the air molecules divided by the molar mass, which I will call it mm, times RT. Now if I could just rewrite this as I will multiply mm on the left side and I will divide by the volume of the container, or the volume of the air molecules, container containing the air molecules. And the reason I did that is because I know that the total mass divided by the volume, that would give me the density of the air molecules. So PV, or PMM, would equal rho RT. Yeah. Okay, so that means the density is just, this is the molar mass, is just P times the molar mass divided by RT. Okay, now since the equation they're requesting has KT instead of RT, I know that from the section that NR, let me actually write it here, NR is the same thing as KT, as NK. And small n is the number of moles, R is just the universal gas constant, big N is the number of molecules of the air present, and K is Boltzmann's constant. Okay, now I need to replace an R, but I don't have an N here, so I could pre-multiply here and here by N. Okay, and the reason being is because now I could replace this NR with NK. Okay, so now my rho becomes P. Now keep in mind that this small n, the number of moles, that's how many grams total of air molecules I have. So that's the mass total of air molecules divided by the molar mass of air, because this is molar mass will give me grams per mole, and above I have grams, so I would get the moles. That's what moles, that's what the number of moles are. And then here I have the molar mass, so these two guys would cancel out, and then this is over Now I can replace small n times r with capital N times k t. Okay, so now this becomes p over kt, and here I have m total over n. Okay, but this the mass total over the number of molecules, that's the mass total of the air over the number of molecules, that would give me the average mass of one molecule of air. So this, we will call this small m, as the question is saying. This is the average mass of an air molecule. Okay, and so with that said, that means the density is equal to p m over kt. And now if I plug in this into the above result, this is the density of air in part A, I would indeed arrive at the required differential equation, dp over dz is equal to minus p m, or let me leave p outside, so this would be mg minus mg over kt times the pressure. Okay, assume we have to verify that the pressure as a function of height would be this, assuming that, now we know that the temperature does change with height, but assuming that T is not changing, which means this temperature here in the denominator is not a function of Z. Okay, that means it's independent of the height Z. Assuming that, we have to derive that. Okay, so this is a first order differential equation. It's linear and it's separable, so we could easily solve it. Let me do it here. So I could divide both sides by p, so dp over p, and I could move the dz, multiply dz on the right hand side, so this would be minus mg over kt dz, and now I could integrate both sides, and these integrals will run me from here I would go from let's say the ground level, sea level, to some altitude z, and to distinguish this from my variable of integration, let me call this z prime, and I would integrate this from p0 to some pressure p at some height z, whatever that is. And so to distinguish this, I would prime my integration variable. Okay, so the first one is ln, integral of dp over p is ln. This is not a prime, this is just prime coordinates, so we will get p ln p equal minus mg. These are constants, they can come outside the integral. Integral of dz is just z from z prime from 0 to z, and this is evaluated from p0 to p, so that means ln p over p0, because it's ln p minus ln p0 equal, and then this is equal to minus mg over kt this is at sea level. Let's just put this in parentheses. Okay, so this is equal to minus mg over ktz, and then I can use the exponential to get the pressure. So p so E raised to the right hand side would give me P over P0, or P equal P0 times E to the minus mg over ktz. This is all on the exponent of E. Okay, so this is my pressure as a function of height. So given any height, I could find the pressure, and then it says show that the pressure obeys show that also the density obeys a similar equation, right? Well, I've already in part A I proved that the density is proportional to dP over dz, right? So using this, using my first equation from part A, what would dP over dz be? I could take the derivative here, so dP over dz would equal P of 0, and then the derivative of E is the same times the chain rule, so I would multiply by minus mg over kt, chain rule times the exponential itself, right? But this here, these two terms here are just the pressure, right? And so this is just equal to minus mg over kt times P. Okay, or let's just leave it as is. Let's see, from the first equation I know that dP over dz equal minus rho air g, so rho air would be, so from the first equation rho air would be minus dP over dz divided by g. Okay, so dP over dz is just that, so all I have to do is kill the g, so I would get minus P0 m over kt E minus mg over ktz. So we can see that the density obeys a very similar equation. Except you just drop out the gravity, but otherwise it's proportional to the exponential of negative constant times the height. Okay, the last part is just basically using this information to figure out the pressure at certain locations. So it's just a matter of plugging in numbers. I'll do one. Let's do the pressure Utah at 1,430 meters. And so 1,430 meters, let me do it here. I know that 1 mole of air weighs, you could easily look that up, or it's in the text, it's 0.02896 kilograms. Okay, and so if I need the mass of 1 molecule, I would have to divide by the number of molecules that I have. That's for 1 mole of air. So I would have to divide by how many atoms, because we said that that's the average mass of the air molecule. So if I want the mass of the molecule, of one molecule, the average mass of one molecule, I would have to divide that by Avogadro's number, because there's Avogadro's number of molecules in 1 mole. So that means, so this would be m in 1 mole. Let's call it m mm. Okay, so if I need my m that I'm using in the question, the mass of one molecule, the mass of a molecule, that would be that 0.02896 divided by 6.02 times 10 to the 23 atoms. That's Avogadro's number. And so that would get me 4.81 times 10 to the minus 26 kilograms. Okay, so now I can plug into my formula the pressure at that height. Pressure at 1430 meters is equal to pressure at sea level, which is 180 m, times the exponential of E. What do we have in the formula? mg, so that's what I had, 4.81 times 10 to the minus 26 kilograms, times gravity, 9.81, divided by k. K is just 1.38 times 10 to the minus 23, and the temperature would be around 300 Kelvin, 27 degrees. And you plug this on the calculator, you would get that the pressure at that altitude in Utah is 0. Oh, there's a minus sign here. And so let me plug this in. Oh, I think I forgot the Z here. So there's a 1430 here, right? Because there's, yeah, the Z. So 0.85 ATM. And the same applies for the last two, except it will be different numbers, different Z. This concludes that question. Problem 116.